Okay, here we are in the lab again, and so we're working on the front end. We're going to try to transfer some data across the bidirectional transceiver, the 74AC245 chip. And so I found a problem, and I was going to check this before I submitted the PCB, but I didn't. So it's another mistake, and it bothers me. But I had to remind myself that it's the fact that we have a PCB in our hand makes us think mentally that it should be perfect. But in reality, it was a choice to do the PCB because in the long run, it's cheaper than doing a prototype. So the PCB we have right now is a prototype. So it's going to have all kinds of jumpers and stuff. It's going to look nasty when we're done. And then we'll submit for another PCB, and then everything else should work perfect. I have to remind myself of that because it's just, you see a PCB and you're like, that thing should work perfect. But it's just a state of mind that times have changed. PCBs are cheap now, so you can just make all the PCBs you want. Not quite, but you can use them in the place of a prototype. I think, for me anyway, prototypes have kind of gone away. It's a through hole type thing. For surface mount, it's more feasible and cheaper just to order a set of PCBs and order it again when you finish your revisions. So anyway, in order to fix it, the problem is that on the schematic, the direction, because it's a bidirectional transceiver, so when you write to the SRAM, then the data flows from the microcontroller out through the buffer, the 245, and it goes to the SRAM. And then when you read it, it goes back the other way. Well, you have to coincide the read write in the SRAM with the read write on the 245 chip, and they have to work the same way. So in order to do it properly, I have to take the 245 chip and turn it around. So that's because the direction is wrong right now. And so there's several ways you can do it, but it's easier to turn it around on the next revision. But we can't do that on our board. So I had to cut one of the wire, the trace that goes to control the direction of the transceiver, and to separate it from the microcontroller, align the read-write signal that goes to the SRAM. So then we have to just, for now, use another port pin to control the direction of the transceiver. And that's fine. That's not going to hurt us. So, but later when we do our revision and order our new PCBs, then it will just be all combined into one signal because it's flipped around. So when the signal goes low, both the SRAM and the transceiver sends information one direction together, and when it's high, it goes the other way. But so right now, since we can't turn the chip around physically on the board and have it work, we're just gonna add another wire to our prototype and go from there. So let's get to it. So the issue is when we come over here to our 245, our bus transceiver, when we write to the memory right here using our read write. So when it's low, that means it's writing into the SRAM, out through our connector to the SRAM on main brain. So when we do that, at the same time, this will come low here. So when pin 1 becomes low on the 245, see the direction, which is pin 1, the data goes from the B side to the A side. So what that means is it goes from this side to this side, which is opposite of what we need. So in order to fix this, you could put in a inverting buffer on this line to invert the signal, or you could disconnect it here and control this line by another port pin, okay, which is a possibility. Or the third way would be to take this and flip it around. So in our revision for the next board, we're going to flip this around. But we can't do that on our PCB, our existing PCB. So it's what we're going to do just for a workaround until we get the next revision done, is we're going to chop this line here and we're going to connect it to the next available I/O pin, which looks like maybe 67 or 44. So let's go over here. And if we look at our microcontroller, so we got 44s right here. And see, there's another issue. This pin goes nowhere, right? Because it's not being used. And the microcontroller is on the opposite side of what our 245 is. All right. So if we look at where our 245 is, pin 1 is right here. And so it connects over here. So if we chop this line here to separate it from the read-write signal, then we have to run a wire from pin 1 to the microcontroller. But the microcontroller is on the wrong side of the board. Okay. So what we're going to do is going to make some more ugly, but it will fix our problem. We'll run a wire from pin 1 of the 245 across the board over to like here somewhere. And then we're going to drill. We have a lot of open space here, so we're just going to drill a hole in the board just big enough to get a wire through. And then we'll run our wire through the hole to the other side of the board. And then come out here somewhere and just run it over here, pin 44. All right. And pin 44 is RE9. All right. So RE9 will control the direction of our bus transceiver until we get our revision, which we will use the same as the original. We'll just flip this chip around. All right. So that's what we're going to do. So that means to drill a hole, I usually do it in the mill, in the machine shop. So we'll go right out into the machine shop today and we will drill a hole and then we'll run a wire and get that taken care of. Then we'll write some code. And I think that should be everything to get our front end test going, I do believe. We will find out. All right, here we are in the machine shop, and we're gonna cut the hole. So this one, there's enough room, you could probably just drill it by hand, but I just wanted to show you how I normally do it. And so the mill cuts a much better hole than a drill bit anyway. So here we go. And that's it. That's how easy it is. And look at the hole. It cuts a really crisp, nice looking hole. That's why I use the mill. Okay, here we are. We have our jumper. And you can see it coming through the board right here, going over here to pin 44. And on this side, we got a big long jumper from pin 1 over here, comes all the way down, goes around through the board, and to pin 44. So then, usually it's customary, you tack the wire down with super glue. It's just keeps it from flopping around, because if it flops around, it's going to break loose. You don't want that. So once it's soldered on, then you secure it with super glue. All right. Now let's get hooked up and write some code. Okay, so before we get started, I want to do a little housekeeping on our code. So we get this info here. It's not a warning or an error, but it just, I don't like it there. It kind of bothers me. So it's easy to take care of. All you have to go up to your project and right click and select properties. And then it's under the compiler, the XC16. So it says it's the data model right here, data memory model. So right here, default is large, so you just put it on small, hit OK. And then when you recompile it, or build it, then it goes away. So we're good on that, okay? Now, I want to take and move all our stuff here, our definitions and our union and our declarations, and I want to move it to our header file over here, IO board H. So we're going to just paste that in there like that. And then we have to include that file. So when you do an include, it pretty much pastes in the code in that file that you include here in there. There we go. And then it should compile okay. We'll have to check it. All right, so we're good. We're moving along good. So then we got to, since we are defining our PMP port, we need to create an a small function to initialize it. So we'll call it PMP init, and it won't need any variables, so it'll be void there as well. And so there's that. So then we want to do our declaration up here and put it in the IO. So they're all going to go in this list. We'll make a list of them right here. And then that ends with a semicolon. All right, and then we'll check it by building it. All right, and then I always clean and build because sometimes it does make a difference. Sometimes it will trick you. All right, so now let's jump over here real fast. Now, what our goal is to, there's pins that are called like PMP, well, not PMP, but PM, and like PMD is data bit, and PMD 14 is data bit 14 for the PMP module. And so it consists of up to 16 data bits and up to, I believe, 16 address bits. And then it has 2 chip selects and a read and a write. Okay, so it's what we want is we are only going to transfer 8 bits of data. So we only want an 8-bit data bus. And if you look at how many address lines we only have 13. So addresses 14 and 15 we don't need. And we have a read and write and an output enable. Okay. And we have a chip select. So then if you look where our chip select goes, right there, then we just have it coming off of a digital pin, a port pin, port D. So we don't need the chip select on the PMP. And our output enable goes to PM read and PM write. So we'll need to configure that, and then we'll have to configure read write too, because it will go to over here to PM write. All right. And you can configure it high or low active, and you can configure it. We'll see. So that's basically the idea. So we're going to run 8 bits of data in and out through this transceiver here into the SRAM, back and forth, in and out of the microcontroller. So that's what we're going to try to do next. Okay. So let's go to our data sheet. And so PMP means parallel main port. And so it has a few registers to control it, to configure it, but we're only concerned with about 5. So the first thing, so when we come over here to our code, so when we call initialize, we call this function to initialize the PMP module. We might have to reinitialize it somewhere down the line in our code. So the first thing we want to do is make sure that it's off. So if we configure it and we turn it on and something happens down the line and we want to reconfigure it, reinitialize it, then first thing we want it to do is to turn it off, because you can't configure the registers usually when it's turned on, when it's active. So you want to turn it off, then configure the registers, and then turn it back on. So our very first thing is to make sure that it's off. So our first register is PM control. And then the first register, the top of the register is enable. So we can use the bits. And once we get all the bits configured, then we'll just write one 16-bit word to the thing, to the module. So, but at first we'll just configure all the individual bits that we want, and then we'll combine them later. So the name of it is PMCon. So come over to our code, and then the first thing we do, we're going to want to make sure that it's off. So PMCon, we're going to do it bit-wise. So it's bits dot on, and that equals 0. All right. And then later on, we'll turn it on after we configure it. So then you should keep good comments. So, all right, make sure the PMP is off. All right, before configuring. Okay. So then the next thing, I like to put spaces between them when they're different registers and stuff. So next up, we have the default when you boot up or reset it is 0 for all of these registers. So if 0 is what you want, we could actually, well, no, we can't. We have to make sure it's off first. So we have to make sure it's off because we might run it later in code. All right, so we had to override this. So we don't have to worry about idle mode. That's if we get into the power saving stuff, we will have to come back to that, but we don't have to worry about that. So we're not going to do any address multiplexing. So we're going to go with the default, which is address and data appear on separate pins. So we have a separate data bus and a separate address bus. If you needed to have more pins available, then you might want to multiplex, but it makes it more complicated and you have to have a latch to separate them out, like the old 8088 type deal address scheme. Because in 8088, the upper address 8 through 15 were multiplexed onto the data bus, and you had to have a latch, and you used an address latch enable signal to tell the latch when to latch the address. So it just makes it more complicated. We won't do that here. We're not set up for that here. So we're going to leave that as 0. We're going to use SMIT triggers inputs for noise in case there's some noise. And so that stays 0. We don't have to do nothing with that. All right, so now the PM write port. I don't think we're going to have to do that. We might have to do that, but we'll just leave that right here disabled, and we'll do the read write strobe here. And so we're going to put that at 1. So we're in this register and this bit right here. So we come over to our code, and since it's the same register, we'll keep it right underneath. All right, and then we select it. This is the read equals 1. Okay. And make sure that's right. PT read enable. All right. So that's we got that messed up. All right. So PT read enable. All right. So we go to our next one, and what do we got? Chip select function. We're not using those, so that comes down here to 0. They function as address bits. Address latch. We're not going to latch any addresses. we're not, no chip selects, and that's just a note. All right, so I think we're good for write at the moment on this one. Come back to our registers. Next one is PMCon H. So the only thing we need to do here is we're going to use dual buffer mode. That makes it kind of like full duplex. So it's only valid in host mode, and that's what we'll be setting here shortly. So we want separate registers for reads and writes. Yes. So we want to set dual buffer to 1. But this is it's a new register. So we'll come over here, skip a line, bits dot dual buffer. And we're going to set that to 1. So we're in dual buffer mode. All right. Now next. That's the only thing we do here. Read start. We won't mess with that yet. So we come back to our list. And so then the next thing is to set our mode. We don't have to worry about this. We can talk about it, I guess. So this sets the address 15 and the chip select or the chip select. And that's selected in the PMCon. And so this register here is only used in the dual buffer. But we're not using the chip select or the addresses, so we shouldn't have to worry about that. So we come over here to PM mode, and we just have to set the mode. Busy tells you when it's reading and writing. It's just a status. We don't have to worry about IRQ. We're not going to do an interrupt. At least not yet. No auto increment. You can set it to where every time you read it, it increments or decrements the memory address so that you can just like blast through a big section of RAM or something. But we won't need that. We're not going to need 16 bits. So everything is good here for the default of 0. This is all our default values here. So 0 is what is the default after reset. So we don't have to worry about that. Now, our mode, we must set it in mode 2. So we won't use the chip select, but we want read and we want write and we want the address and we want the data 0 to 7. So it has a note 3 up here. These pins are active when mode 16 equals 1, and they're not. So we won't have to worry about that. But so we'll be in host mode 2. So we got to set that in our code. All right. And so that is PM mode bits dot mode equals 2. Okay. And then we have to set what address lines we're going to use. And we're going to use all of them except for 14 and 15. So if we come over here to PM address, these registers here are used for transferring data in and out. We don't configure them. We just use them for bringing data in and out. So we'll get to that. PM status, that's a status you can read. It gives you certain statuses of what's going on. The register, the input buffers are full and overflow status and blah, blah, blah. All right, so we don't have to worry about that. And this is some more reading and writing, which we'll get to. So the only thing we have to do is set the addresses. So by default, they're all turned off, which means they're I/O pins. So we need to turn them on. So we need to turn on all of them. So we're going to write a 16-bit value to this whole register in this case. So we're just going to take this register here and put it over here. And so you just come here. And then instead of using bits, we're just going to write to the whole thing. So we're going to use all the bits, all the address except 14 and 15. So that would be in binary, it'd be 001, whoops, 1 1 1 1 1 1 1 1 1 1 1 1 1, right? So that's what it would be like. But we're going to write it in hex, so that is 3FFF. So let's do this hex number. Oh, X means hex. And so that's 3FFF. All right. End of a semicolon. Okay, so then at the end here, we want to enable it. And so we'll just copy that down here and make that a 1. So that'll turn it on. So let's get some comments up here just so we know. All right, so this is the read line, we can call it for right now. And this is set dual buffer mode. And then this is set host mode 2. And enable addresses 0 through 13. All right. And then turn on the module. Okay. So that's pretty much set there. Let's do a test compile here. Oh, we got some errors. Yeah. So the problem here is it has on, and over here in our header file we defined on already. So you could change this because you could add like something onto it like that to define it, but that kind of makes it more confusing, and we're trying to keep it less confusing. So we can use a preprocessor and turn that off while it's doing this. So it's what we're going to do is we're going to do just set the bit. That way we don't have to like undefine the on and then redefine it and then check if it is defined and if it's not defined and this and that. So we're just going to set the PMCon bit. So if we come over here and PMCon, so this enable disable one is bit 15. So that means we can just do this. We want a bitwise OR. All right, and then we're going to set it to a 1. And then that is bit 15. Actually we need to set that as a 0. And that's how you set that. And then we'll do the same thing down here to turn it on. And that's kind of maybe a new command for some folks. So just have to look at the C reference and look that up, and it'll explain it probably better than I can. Oh, I don't think that worked too good. So we want to take this, copy over here, paste, and then we're going to make it a 1. And I kind of like to have spaces a lot. I like spaces, so we'll do this. It doesn't make any difference. All right, so now if we compile it, it should work. All right, so it likes that better. I think that's the simplest way to do it without changing other stuff. Because if you change the definition of on up here in the header file, then you have to change it all through the code, which we don't have that much code, but still. So that's the simplest way to do that. And you can do that on these too. And this is a more acceptable way to do it, except it's less, you can't, it's harder to understand because this is a lot easier. It's like mode 2, but if you just set the bit, you're like, well, what bit is that? So without your comment, it's like, I don't know what's going on. But I think this is good for right now. I think we can kind of understand it. So then, the next thing we want to do is we got to change this up here, the heartbeat. And I changed it. I didn't get it on video for some reason. But anyway, we want to change our heartbeat to LED 0. So we'll just do it like that. And because we want to get it away from RE4, port E, bit 4. We want to get away from that because we're using that for other things. So then another thing that we want to do, we have to call this initialization code or it's not going to initialize it, right? So let's copy that, bring it up here. So we want to do that before we start the main loop. So up here, well, actually it has to be in the main loop, but we want to do it after we do the oscillator and probably all the way down here. Probably is fine. So we just call it just like that, and that'll initialize our PMP. And so then we want to do something. So we'll do it through the loop. So it just keeps writing it. And it should show up on the scope better that way. The address is once you write to the address, it holds it there until you change it. But the data just does the strobe on the read and write. So if you just keep doing it over and over, then you can see it on the scope better. So we want to write to PMP. So we come over here to our registers. So we have PMD out 1 and PMD out 2. And so what we have here is, so it's a 16-bit register, but we have it set for 8. And these are for 8-bit read operations in client mode and write operations for dual buffer host mode. And that's what we're in, dual buffer host mode. So we're going to use this register to write data to the PMP. So this is PMD out 1. And we'll come over here to our code. So we'll just do this. And to write to it, you just tell it what the value is and it sends it out on the port. So we will just go we'll just start with 3 and just see what happens. Well, we got to check all different numbers and stuff anyway. So we'll do that. And that should send something out onto the port. And then the only other thing we have to do is we have to do a read write, but I think this will actually should put something out on the port. So I think that's minimum requirement right now. All right, so that's our code. That's our firmware. So let's do a test build here. All right, it likes that. So we'll just send it to the IO board now. Now the first time that you do it, it takes a little longer. Oh, and I should show you guys. Let's get that finished. Okay, so it sent it and programmed it. But if you come over here and you go to your PIC kit or your snap or whatever you're using, then it should allow you to tool options or program options. Program options, no. Tool options. Yeah. So then program speed, you can select low, normal, or high. And if you select high, it will program faster for you. So that speeds things up a little bit. All right. I get rid of that for right now. Okay, so I think we're ready to go look at our board with the scope. All right, so we have our LEDs on. We have the green one, which is our just the one we turned on in our previous video. And then we also have LED 0 lit. So that means it's getting something to it, and it should be a square wave that represents our heartbeat. So let's take the probe and take a look at it and see what we got. Because you guys probably can't tell, but it's like not as bright as the other ones. I should have done another red one next to it to show the difference. But anyway, stick our probe on here. If I can do it. There we go. And that's a pretty nice looking square wave right there. So you notice the frequency is a little bit lower than last time. And that's because we added another, we're calling, we're doing the heartbeat plus we're setting sending data out on the PMP. So that makes it a little bit longer time for a loop, for our main program loop. So every time you add code into that main program loop, then the frequency is going to go down. So if you have a lot of code in there, you're going to have a low frequency. But right now, yeah, that tells us that we have that our microcontroller is running and it's running our code in the main loop and everything looks pretty good. So now let's move over and see if the data is coming out on our pins like we expect it to. Okay, so let's take a look at pin. So PMD 0 and PMD 1 should be high and the rest should be low. So if we look at pin 74, 75, 76, and 78, then that will tell us. So 78 is PMD3, so we can get that real easy. These pins are so tight. So this is pin 80, so then 79 and 78. Okay, that should be low, and it is. And so 76, so 77, we skip 76 is low as well. That's PMD2. So the next one should be high. If I can get on it right here. So that's PMD1, which is 75, and it's high like we expect. And next one over is high, which is 74, PMD0. All right, so that looks good. Now, to make it easier, I want to put the data through the 245 onto our connector. So the pins are easier to get to on our connector. So let's go back to our schematic, take a look, and then we'll change the code. And that should wrap it up for this video to get some data onto here through our 245. Okay, let's go to the schematic. So in our data sheet, this is a schematic for our current prototype. So this isn't our new latest revision, but so that's what we want to do. We want the data from here to go through here onto our IO connector so that we can measure it better, easier. So we have on our prototype board, we have this connected to RE9, so port E bit 9, pin 44. So we want to set that voltage level here, our logic level, to make the data go from A side to the B side. So we'll have to look at our data sheet real fast. So we'll pop over here. and scroll down to our logic chart, our logic diagram here. One of these places. Maybe I'll go a little faster here. Right here. So from A to B, our direction has to be high. So RE9 has to be high. So we'll jump over to our code. And up here, before we start our loop, and before we start our initialization of our PMP, it doesn't matter too much, but it's good to do it before. And I don't want to put it in the PMP initialization function because this is only temporary for this prototype board. Our next revision, we won't need this RE9. So first we want to set it as a digital out. So tris e bits dot RE9 equals 0 for output. And then on our port pin, port E bits RE9, we want that to be a 1, a high, okay? So that should do that. So then let's send that to the IO board. Okay, so then we can measure that and see if it's actually there. So that's pin 44. So let's go to our board. So let's check pin 44. So there's 20, 40. So 44 is easy because that's where our jumper wire goes. So if we check that, it is now high. And that's what we want. That is very good. Okay, so there is one more thing. So we have our SRAM. We got to make sure that it's not trying to send data back to us. It needs to be in the read modes before we enable it. So the read write is right here. And so it's going to the PM write, okay? So that is pin 65. So I'm going to make a note of that. That's right. And that is 65. Okay. So now I'd be really happy if we could use RC5. We're going to have to check our configuration, but we should be able to use RC5. All right. And so is what the idea with that is so that we can get the read write here to a write so that the SRAM is accepting data, not shoving data back at us. We just want to do that. That's the next thing we have to do before our final test. So we'll want to go to the code and make it so. And we come over here and we want to do RC5. So we want to make it an output. Right. Equals 0 for output. Then we want to do port C RC5. All right, so now it's active low for a write, so we want to make it 0. All right, so that's a 0. And now we'll just send it to the IO board real fast. All right. Okay, so Our read-write signal is on pin 6 of our I/O connector. And so, and we expect it to be low. So 1, 2, 3, 4, 5, 6. And it is low, okay? And so now we can put our address select jumper to activate our card on address 0, like we did before in previous videos. Now that should activate all the buffers and the SRAM. So on our data bit 0 and 1 should be high, the rest of the data bits should be low, and data bit 0 and 1 are pins 16 and 17 on our connector. So let's count some pins and take a look. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And it's high like we expect. 17, high like we expect. 18, low like we expect. And one more for fun. 19 is low like we expect. All right, very good. Very good. So it looks like we're doing pretty good. And our jumper worked, and we're writing data through the bus transceiver to the SRAM. And we have to go dive into that a little bit deeper and make sure we're seeing what what we're seeing is actually true, because we haven't toggled some of those lines yet, so they could just accidentally be at the state that they're in that we wanted, but it looks good. And so we'll test some of that later, and we want to get data going back and forth bidirectional through that transceiver. We got to be able to read and write to the SRAM reliably, consistently. And so that's pretty much the front end. We'll have to test the addresses, but that'll be with the read and writing to the SRAM. So we might have to configure the read and write line of the PMP a little better. But that's pretty much it for the front end until we get a new revision board in, and then we can stick two of them together in the same on the same ribbon cable, and see if we can address them, see if they work in the system together, and mainbrain can address them separately and stuff like that. That's down the line. So then after we finish our front end, then we'll start on our I/O stuff, our digital potentiometers and switching, using our MOSFETs to switch, stuff like that. But yeah, right now, so that's it for this video. In the next video, we'll jump into finalizing our front end and move on from there. So I will see you in the next video.